All right, section 3-8 is on the derivative of sine and cosine, and as you may recall, the objective of this section was to derive the trig rules for the derivative of sine and cosine, which for the most part we've covered. There was one little part there that we skipped over, and that was that limit as x goes to 0 of sine of x over x. And we showed on the calculator graphically why that limit looks like it's going to 1. We also looked numerically why that limit looks like it's going to 1. But that's the piece we want to focus on today and look at it from an algebraic standpoint as to why that limit is in fact equal to 1. All right. So in order to do that, we need to actually come up with a relationship between 3 different areas here. And so let's take a look at what areas we're dealing with. This little sketch here illustrates or shows a unit circle, or actually it's a quarter unit circle. It crosses the x-axis at 1 and the y-axis at 1. And then we've got an angle marked that has a terminal side. This right here is the terminal side of that angle. And where that terminal side there crosses the circle, that quarter circle, we drop a vertical line there, and we're measuring that distance as v. And that horizontal distance from the origin to that vertical line, we're measuring that as u. And so that creates here for us just a little right triangle that we'll put in red here, that little right triangle that has legs of u and v and a hypotenuse of 1, because it's the unit on the unit circle, and the radius of that circle is 1. And the hypotenuse is a radius of that circle. It also has this sector. The sector is this pie-shaped piece right here, whose sides are equal to 1 because it's on a unit circle. And then finally you have this larger triangle here. I've already marked the hypotenuse of it. If we drop this vertical line here that goes down to the x-axis and touches the x-axis at x equals 1. Then we mark that vertical distance there as z, and it turns out then this is actually a radius of that circle. Then the horizontal leg of that triangle is a radius of that circle, which means that it's equal to 1. So the first thing I want to do is look at how u, v, and z are related to this angle x. So it really doesn't matter what we start out with, but let's look at this small triangle to start off with. A small triangle. I'll just draw a triangle there for small triangle. And let's start with u. Let's just do this in order here. So if I look at u and I look at this angle x, u is the adjacent side to that angle, and the hypotenuse of that little red triangle is 1. So if I've got an angle at an adjacent side and hypotenuse, that sounds like cosine. If I take the cosine of x, that would equal u, the adjacent side, divided by 1, or that's just u. So it turns out that the horizontal leg of that little triangle is actually equal to u, which turns out to be equal to cosine of x. Now if you look at the vertical side of that triangle, the vertical side and the hypotenuse there would give me sine of x is equal to v over 1. Of course, v over 1 is just v. So it turns out that the vertical side on that little right triangle is equal to v, which is equal to the sine of x. All right, now if you look on the big triangle, some similar properties show up here. That if I look at my angle x again, and the vertical side of this is z, and again remember the horizontal leg of this is the radius of my circle, which is 1. So that sounds like tangent. If I take the tangent of x on that big triangle, I will get z divided by 1, or that's just z. So it turns out on the big triangle there, the horizontal leg is 1, and the vertical leg, which is equal to z, turns out to be equal to the tangent of x. Now we're going to use those values, u, v, and z, in just a minute here. But what I want to set up first of all is an inequality, a double inequality, representing the relationship between the areas of these 3 different geometric figures. So first thing you have is I can see that the small triangle small red triangle there is the smallest, and it fits inside of the sector. And then that sector fits inside of that big blue triangle. So the property that I see here is I've got the area of the small triangle. That's the smallest of those three areas. That's less than or equal to. The green area there is that sector, the area of the sector. And then finally, that's less than or equal to the area of that big triangle there, the one that's marked in blue. Okay, so just based on our sketch there, and the fact that the red triangle is inside of the sector, which is inside of the blue triangle, I can come up with this double inequality. Now let's see if we can actually find the area of each of these and fill in the details here. So let's start with the small triangle. So the area of the small triangle, the base is u, the height is v. So the area of that small triangle area is, of course, 1/2 base times height. So it's 1/2 u times v. And that's less than or equal to the area of the sector. Now, the sector there is actually just a fraction or a portion of the whole circle. Now, I know how to find the area of an entire circle. The area of a circle, of course, is pi times the radius, which the radius in this case turns out to be 1, so it's pi times 1 squared, but it's not the whole circle. It's only a fraction of that whole circle. So the way to find the area of the sector is just multiply the area of the whole circle by the fraction of the circle that we're working with. Well, the fraction of the circle that we're working with is based on this angle. The angle that we're working with is x, and that's x out of a full circle of 2 pi. So if we take x over 2 pi and multiply it by the area of the whole circle, that tells me the fraction of the circle we're working with, the area of that sector. And that's less than or equal to the area of the big triangle. Now the big triangle has a base of 1 and a height of z. So the area is 1/2 the base, which is 1, times the height, which is z. Okay. So there is our double inequality. Now let's fill in the what u and v and z are equal to based on the work that we just did. If you go back up here, we said that u was equal to the cosine of x. So let's replace u with the cosine of x. And we said that v was equal to the sine of x. So we have 1/2 the cosine of x times the sine of x. And that's less than or equal to, we'll just simplify this here in the middle. I can see that the pi's will cancel out, and you have then 1/2 x times 1 squared, that's just 1/2 x. And that's less than or equal to, on the right there, we have the 1/2, the one I won't worry about writing down, but the z, remember we found out that z was equal to the tangent of x from our big triangle. So that's the tangent of x. All right. Now what I want to have happen here is I want the middle of this double inequality to turn out to be that that limit function we're trying to analyze. We're trying to analyze sine of x over x. So I want to do some things to this so that the middle of this becomes sine of x over x. That's the goal. So the first step that I see is I can multiply through by 2. And basically what's going to happen is the 1/2s are going to cancel out when I do that. Multiply everything by 2. All right, the next step of this is I want to get sine of x over x in the middle, so I'm going to take and divide everything by the sine of x. So when I divide everything by the sine of x, of course when I'll go ahead and write it that way. When I take cosine of x times sine of x and I divide it by the sine of x, some nice things are going to happen there. You can see the sine of x's are going to cancel out. I'll divide this middle term here by the sine of x. And I'll divide the last term here, which is tangent of x over the sine of x. Now, I don't quite have in the middle what I wanted. I wanted sine of x over x, but I have the reciprocal of it, so we're close. Again, a couple things that you'll notice. First of all, the sines will cancel out over here. And if you will, tangent is equal to sine of x over cosine of x. And that's all divided by this, this is equal to that, I should say, and I shouldn't try to indicate so this is equal to the sine of x over cosine of x, and that's all divided by this sine of x. So you'll see here the sines will cancel out, which ends up giving you 1 over cosine, or that's actually secant. So let's write it that way. I have the cosine of x is less than or equal to x over the sine of x, which is less than or equal to the secant of x. And what I wanted to have in the middle was sine of x over x, so really all I have to do is reciprocate this whole thing. So if I reciprocate everything, I'll have 1 over the cosine of x. And when I do that, realize the inequalities switch direction here. So this becomes greater than or equal to sine of x over x, which is greater than or equal to 1 over secant of x. We'll go ahead and write it that way initially, and then we'll rewrite this. So the last step of this, 1 over cosine is the secant of x is greater than or equal to the sine of x over x, which is greater than or equal to 1 over secant is known as cosine of x. So there we go. I have that sine of x over x is between cosine of x and secant of x. And we're going to use that property here in just a second. Okay, so that's the first thing I need to notice. Based on that relationship from those areas, I can deduce this property. All right, now the theorem that we're going to actually use to prove what this limit of sine of x over x as x goes to 0 is equal to is called the squeeze theorem. Sometimes it's referred to as the sandwich theorem is another way that we describe it. But squeeze theorem, as its name indicates, we're going to try to squeeze one function in between two other functions, which kind of gives you a heads up as to why we just went through that process and showed that sine of x over x can be squeezed between secant of x and cosine of x. But here's the theorem. There are 3 conditions or 3 hypotheses that you have to meet in order for the conclusion to be true here. The first one, it says if g of x is less than or equal to h of x for all x close to c. But you don't have to worry about what's happening right at c. Okay, so you have to come up with 2 functions, g and h, and show that function g is less than or equal to function h for x close to c. The second condition is that you have to be able to show that the limit as x goes to c of g of x is equal to the limit as x goes to c of h of x, which we'll call L here just for ease of writing later on. So you have to show that the 2 limits are the same as x goes to c. And the last piece there, the third condition, is that g of x has to be less than or equal to f of x, which has to be less than or equal to h of x. That's where you're squeezing f of x in between g and h. That's the name of the theorem. So you have to show that f of x can be squeezed between g and h for all x close to c, but again, not equal to c. We don't have to worry about what's happening right at c. If you meet all 3 of those conditions, then it turns out the conclusion of this is that the limit as x goes to c for function f, limit as x goes to c of f of x, is also equal to L, the same limit as g and h had. Now, when you look at that theorem, and for that matter, when you look at any theorem, if you look at the conclusion, sometimes the conclusion will kind of hint you towards where what the purpose of this theorem is or where you might use it. So the conclusion here is just about the limit. It's the limit as x goes to c of f of x is equal to L. And we've learned several techniques for finding the limit. Substitution and factoring and so forth. And by all means, if those methods work to find the limit, then use those methods. Those are much easier than using squeeze theorem. The reason that we have squeeze theorem is if the function f of x is so complex that I don't have a method for finding what the limit is equal to, and I need another technique that I can use. That's what this limit is for, or that's what this theorem is for. And so what it relies on is my ability to come up with 2 other functions, g and h, whose limits I know, based on the second condition here, that I have to know their limits are both equal to L. And if I can show my function can be squeezed between those 2, then my function must have the same limit. Okay? That's the whole idea of using squeeze theorem. Use it for a function that is too difficult to work with on its own for finding a limit, and instead work with two other functions, g and h, that are much easier to work with. Okay? And that's what this little note here says. Use this to find the limit as x goes to c of f of x when f of x is too difficult to work with. And what kind of functions are too difficult to work with? Well, we're going to see one right here. That limit as x goes to 0 of sine of x over x. I don't have any way, any algebraic technique I can use to simplify that any further. And instead I'm going to rely on this theorem to prove that that limit is equal to 1 by finding two other functions whose limits are 1 that can be this function is squeezed between. All right, so let's look at the limit property and its proof here that in fact it's equal to 1. So this is the property that we said we were going to take a look at and find or show algebraically that the limit is in fact equal to 1. The limit as x goes to 0 of sine of x over x is equal to 1. We use that in the first half of this section to show that the derivative of sine is in fact cosine. And now I want to show you how we know that in fact it is equal to 1. So we rely on the squeeze theorem. Okay, and I usually like writing the theorem that we're going to use before we start, and then I'm going to list the conditions here that we've got to meet and show that we meet each one. All right, so the first condition was that you have to come up with two functions, g and h, and be able to claim that g of x is less than or equal to h of x. All right, well, we've actually already did that. We're going to let g of x be the cosine function, and we're going to let h of x be the secant function. And we've already shown that cosine of x is less than or equal to the secant of x for all x. But the theorem said we only have to worry about values of x close to 0 in this case, but it actually works out for all x. And again, just to jump back here to what we did with this area relationship, we've already shown, if I kind of get rid of what's in the middle here, I've already shown that cosine of x is less than or equal to secant of x. We've already done that. So I don't need to go through that whole thing again, but if I wanted to, I'd go through those exact same steps that I just did. All right, the second condition is about the limit. So the second condition is the limit as x goes to 0 of the cosine function, which as x goes to 0, cosine as x gets closer and closer to 0, cosine is crossing the y-axis up at 1. So the limit of that function is 1. Cosine of 0 is equal to 1. Check out the limit as x goes to c of, or x goes to 0 of the secant of x. So I might not remember what secant's doing as x goes to 0, so I could rewrite this as the limit as x goes to 0 of 1 over cosine, if it helps you, which I think it does. And so as x goes to 0, you end up with 1 over the cosine of 0. Again, cosine of 0 is going to 1, so 1 over 1 is 1. So we've met the second condition. The limit as x goes to 0 for cosine is equal to the limit as x goes to 0 for secant. And now the third condition is that you have to be able to show that f of x can be squeezed between g of x and h of x. And we have already done that, actually. We have already shown that cosine of x is less than or equal to the sine of x over x, which is less than or equal to the secant of x. Again, that was that area relationship. If I just flip back a couple slides to show you again, we went through this and we found out that sine of x over x can be squeezed between cosine and secant. So we've already met the third condition based on the work we've done previously. So thus, by squeeze theorem, the limit as x goes to 0 of sine of x over x must be equal to the limit of my other two functions. My other two functions are approaching 1, so this limit must also be equal to 1. And there's the algebraic proof. It actually relies on squeeze theorem to prove it. Okay? And that is the end of this second half of the section.